Alrighty, welcome to Blue Penley. State what's meant by the EMF of a cell. I think I missed a mark on this one. I didn't quite, it's like these definitions. Is it important? But anyway, this is what they're looking for, right? EMF is like voltage, right? So it has the EMF is in volts. Remember, a volt is a joule per coulomb, right? Okay. So what you need to say is that ultimately it's the EMF is how many joules of energy it gives a coulomb of charge, right? So it's the energy per unit charge that it gives in moving, and this is the part I missed, in moving charge from one terminal of the cell to the other, right? So it's the energy or work done moving the charge per unit charge, right? So that's per unit charge, right? From one terminal to another. I got the like joules per coulomb part, but I didn't say from one terminal to another, and you had to say that, and I didn't say it. I'm very sorry. You deserve a better teacher. In general, that's true, but there it is. All right, and then they show, they say that this is 1 meter of wire, 1.0 meters, right? And this is 0.35, AC is 0.35. Well, this wire has a uniform resistance, right? Okay, so if I put it exactly in the middle, it'll be exactly half of 80 ohms, right? This wire would be, if I put it 1/10 of the way up, it'll be 8 ohms, okay? So the concept here is that the length of it is proportional to the resistance, right? So we could say that 0.35 is to 1 meter, right? As that resistance is to 80 ohms, right? And then solve. So you have to, the two marks are, you need to say that the resistance is proportional to the length of the wire that you have, right? So if the C is all the way up here at B, then it's 80 ohms. If it's halfway, it's half of 80. If it's 1/10 of the way, it's 1/10 of 80, right? Okay, and then you have to show the calculation, okay, and that's how you do it, right? Then it says determine E, right? And what they say is that they've got it so that to measure the EMF of a cell. Oh, the current in the cell is 0. There we go. Okay, so this is the cell. I was like looking for it. Somewhere they tell you that the current is 0, right? Well, if the current is 0, then that means that the potential at C is exactly equal to the potential of this guy, right? Okay. Maybe that's one of the marks, right? So the potential right here on this whole thing is going to be the potential of this cell, right? So then, then the question is, what's that potential? Well, we can do another ratio here, right? We can either do the 0.35 to 1, or we could do the 28 ohms to the 80 ohms, right? But just imagine if I've got this resistor like this, right? And I have let's say I've got this giant resistor. Let's take the other things out of it, right? This is going to be 12 volts. This is going to be 0 volts, right? So if I take a voltmeter and I compare this voltage to this voltage, and I look at the very bottom of this, right? Okay, or the top of that, right? I will get 0 volts. If I go halfway through, I'll get 6 volts. If I go all the way to here, I will get that there's actually 12 volts, right? So as I move this arrow down, I'm getting more and more of this. Potential that's on this thing, right? Okay. So now what I'm looking for is I need to set up a ratio, right? And it's 28 ohms out of 80, right? So 28 ohms out of 80 ohms, right? And then that is times that 12, right? So I'm 28 eightieths of 12 there, right? Now, you don't have to actually do that. You could actually do this using Ohm's law, right? We could say 12 divided by 80 would be that current, right? So 12 is that current. I get 0.15 amps, right? And then it's going through 28 ohms, so times 28. And I can get the answer that I got, right? But you can also just do it with a proportion, okay? Now let's go to the next page, right? This is kind of funny, right? It says Cell X is replaced by a second cell of identical EMF, but it's got resistance, right? So this cell now has like a resistor there, right? And it says, what will that change where we have to put this to make this be zero, right? And of course, my initial answer was no. Okay, and here's why. That is the correct answer, right? And here's why, is that if there is no current flowing in this loop, resistors don't matter. If there's no current flowing in this loop, resistors don't matter. And that's because all resistors do is make the voltage drop. V is IR, right? Right? And if the current is zero, then the voltage change across here is zero. Voltage only changes on a resistor when there's current. And remember, in this thing, they tell you that the current in cell X is zero, right? So it's a trick question. They're trying to get you to second guess yourself. Now, to be honest, I honestly, was doubting my answer, and I really didn't want to like post something on the internet where I've got like the wrong answer, and then all these, physics people will be like, right? So I actually set up one of those circuit FETs, right? And I set it up like this, and I had a resistor here and a resistor there, and I made it so there's zero current, and then I had a resistor here that I set to zero resistance, and then I changed the resistance, and of course it doesn't change, right? But anyway, there you go. Hope that helps.